What is a wormhole? Wormholes are hypothetical tunnels or shortcuts in the fabric of space-time. They represent a speculative concept derived from the mathematics of general relativity, which is Einstein's theory of gravity. According to general relativity, the fabric of the universe is a combination of 3 dimensions of space and 1 dimension of time, known as space-time. Wormholes involve bending and warping this fabric to create a tunnel-like structure. The equations in general relativity describe the curvature of space-time in the presence of mass and energy. By manipulating these equations, physicists have found possible solutions that describe wormholes as bridges connecting different regions of space-time. While the mathematics of general relativity allows for the existence of wormholes, their actual existence has not been confirmed by empirical evidence. Nonetheless, scientists are fascinated by the possibility of their existence and continue to explore the theoretical implications. Theory of wormholes. The theory of wormholes comes from the realm of theoretical physics, particularly within the framework of Einstein's general theory of relativity. In this theory, gravity is described by the curvature of space-time, and wormholes are theoretical structures that could manifest as shortcuts or tunnels through this curved space. A wormhole is often visualized as a bridge connecting 2 distant regions of space-time, or even different universes. In this concept, the wormhole acts as a conduit that bypasses the usual 3-dimensional space, potentially allowing for faster-than-light travel or the traversal of vast cosmic distances in a shorter time. Wormholes arise from the idea that space-time can be distorted, stretched, or curved due to the presence of massive objects or intense gravitational fields. The curvature of space-time is described mathematically by Einstein's field equations, which provide a framework for understanding how matter and energy can warp the fabric of the universe. In certain configurations, the curvature of space-time can take on a specific shape that forms a throat or tunnel-like structure. This throat connects 2 separate regions of space-time, and if it remains stable and traversable, it could potentially create a wormhole. Einstein-Rosen bridges. The first mathematical solutions for wormholes were found by Albert Einstein and his colleague Nathan Rosen in 1935, called Einstein-Rosen bridges. These solutions utilize the properties of space-time curvature to describe a wormhole-like structure. However, these initial solutions were non-traversable, meaning they would inevitably collapse or be impossible to enter or traverse. Later on, physicists such as Kip Thorne explored the concept of traversable wormholes. Despite the theoretical possibilities and mathematical solutions, there are numerous challenges and unanswered questions regarding wormholes. The existence and properties of exotic matter necessary to stabilize wormholes remain speculative and unconfirmed. The tremendous amount of energy required to both create and maintain a traversable wormhole is currently beyond our technological capabilities. Traversable wormholes may introduce causality violations or paradoxes, such as time travel and violations of the known laws of physics. Resolving these issues remains an active area of research and speculation. Traversable versus non-traversable wormholes. Traversable wormholes. Traversable wormholes are hypothetical structures that, in theory, could connect 2 distant regions of space-time or even different universes. The term traversable refers to the possibility of being able to travel through these wormholes. The idea is that one could enter one end of the wormhole and emerge from the other end, potentially reaching a different location or even a different time. For a wormhole to be traversable, it would need to possess several specific characteristics. First, it should have a sufficiently large throat or tunnel that remains stable and open, allowing for the passage of matter or information. Second, the wormhole should have a mechanism to prevent its collapse or instability, such as exotic matter or negative energy, which theoretically counteracts the immense gravitational forces. However, the exact nature and properties of such exotic matter remain speculative and unconfirmed by current scientific knowledge. Traversable wormholes have garnered significant interest in science fiction literature and popular culture, often depicted as shortcuts or portals for interstellar travel. However, as of today, there is no empirical evidence or confirmed theoretical framework to support the existence of traversable wormholes. Non-traversable wormholes. Non-traversable wormholes, also known as Einstein-Rosen bridges, are solutions within the framework of general relativity that describe wormholes but lack the properties necessary for practical transportation. These wormholes still connect 2 distant regions of space-time, but they are not traversable due to various factors. Non-traversable wormholes typically suffer from extreme gravitational forces at their mouths, making it impossible for anything to pass through without being crushed or destroyed. They exist as mathematical solutions and can be useful for studying certain aspects of theoretical physics, such as quantum gravity or the nature of black holes. While non-traversable wormholes may not allow for actual travel or transportation, they provide valuable insights into the underlying principles and properties of space-time, as well as contribute to the ongoing exploration of wormhole physics. Wormhole connection to black holes. Black holes, as predicted by general relativity, are regions in space where matter is so densely packed that the gravitational pull becomes incredibly intense. They have an event horizon beyond which nothing, not even light, can escape. While black holes are still not fully understood, they have been extensively studied, and their properties have provided valuable insights into the nature of extreme gravitational phenomena. One intriguing idea is that black holes could potentially be connected to or involved in the formation of wormholes. This concept is based on the theoretical notion that a black hole's intense gravitational field may create a throat that could lead to another region of space-time, potentially connecting two distant points or even different universes. However, there are many challenges and unknowns when it comes to this connection between black holes and wormholes. For example, it is still uncertain whether traversable wormholes are possible within the framework of physics as we currently understand it, or if they exist in nature at all. Additionally, the stability and structure of wormholes, especially those connected to black holes, remain open questions. To explore these connections further, scientists have been investigating the behavior of space-time near black holes, particularly at or near the event horizon. These studies involve examining how matter, energy, and space-time interact in the extreme conditions surrounding black holes. They involve mathematical modeling, simulations, and observations of phenomena such as accretion disks, jets, and gravitational waves associated with black holes. By studying black hole physics and the effects of intense gravity, researchers hope to gain insights into the nature of space-time near extreme gravitational regions. This understanding may help in unraveling the mysteries of wormholes, their potential connections to black holes, and the underlying physics that governs these fascinating cosmic phenomena. It's important to note that while black holes and wormholes are conceptually intriguing, much research and exploration are required to conclusively determine their relationship and whether traversable wormholes are even possible. The scientific community continues to make progress in understanding these phenomena, and future discoveries may shed more light on their connection. Are wormholes stable? Wormholes are theorized to be regions of space-time with a distinct curvature that creates a shortcut or bridge connecting two otherwise distant points or regions. However, achieving and maintaining the stability of a wormhole is a significant challenge. The main issue stems from the inherent instability caused by the curvature of space-time necessary to create a wormhole. According to Einstein field equations of general relativity, energy and matter directly influence the curvature of space-time. For a stable and traversable wormhole, the curvature must be carefully balanced to prevent its collapse or other undesirable effects. This is where exotic matter enters the picture. Exotic matter is a theoretical form of matter that violates conventional energy conditions, particularly the weak energy condition. The weak energy condition states that the energy density measured by any observer will always be positive, and the energy flux must be non-zero. Theoretical studies suggest that exotic matter with negative energy density or negative pressure could help stabilize a wormhole and keep it open. This negative energy would counteract the natural tendency for the wormhole's gravitational field to collapse under its own curvature. Essentially, it would act as a negative mass that counterbalances the positive mass of the matter nearby. However, the existence and properties of exotic matter are still purely theoretical, and it is not yet known whether such matter can truly exist or be generated. The requirement for exotic matter is one of the major challenges in contemplating the plausibility of traversable wormholes. Moreover, the source or creation of exotic matter is an open question. Scientists have proposed various hypotheses, such as the potential for quantum field effects or the manipulation of quantum vacuum fluctuations. However, these remain speculative and require further investigation and understanding. It's important to note that our current knowledge and understanding of wormholes are primarily based on theoretical models and mathematical formulations. Observational evidence or experimental verification of wormholes or exotic matter is yet to be achieved. Scientific discoveries and observations. Currently, there are no known ongoing scientific experiments or research directly focused on creating or studying wormholes. This is mainly because the existence of traversable wormholes remains purely theoretical, and no empirical evidence has been found to confirm their presence. However, scientists are actively engaged in related areas of research that could potentially shed light on the nature of wormholes and their underlying physics. Researchers continue to study and refine the mathematical framework of general relativity, which is the theory that allows for the possibility of wormholes. Investigations into the nature of black holes and the behavior of space-time near their event horizons provide valuable insights into extreme gravitational phenomena. Some theories have suggested that wormholes could be connected to or arise from black holes. So the study of black hole physics indirectly informs our understanding of potential wormhole properties. The search for a theory of quantum gravity, which aims to merge quantum mechanics with general relativity, is an active area of research. Investigating these theoretical ideas contributes to our understanding of the fundamental nature of space-time and its potential for wormhole formation. While direct experimentation on wormholes is currently beyond our technological capabilities, advancements in these related fields contribute to the broader understanding of the underlying physics and could potentially lead to new insights in the future. Practical application of wormholes. One of the most popular concepts associated with wormholes is the possibility of using them as interstellar shortcuts. If traversable wormholes exist, they could potentially connect distant parts of our own universe or even different universes. This could open the possibility of rapid and efficient travel between cosmic locations that would otherwise be impractical or near impossible to reach with our current technology. Wormholes could also play a role in theories related to time travel. If traversable wormholes exist, they could connect to different points in time, allowing for potential time-traveling scenarios. However, the concept of time travel through wormholes comes with its own set of paradoxes and challenges that are not yet fully understood or resolved. Another proposed use for wormholes is in gathering information about far-reaching regions of the universe. By sending one end of a wormhole to a specific location while keeping the other end near Earth, we could potentially observe distant galaxies, phenomena, or even different eras of the universe more directly. Studying wormholes could greatly contribute to our understanding of fundamental physics. Investigating their properties, stability, and connections with other areas of physics could lead to new insights and advancements in the fields of general relativity, quantum physics, and the unification of different fundamental forces. It's important to note that all of these uses are highly speculative and rely on the assumption that traversable wormholes exist, can be stabilized, and can safely accommodate passage through them. While the scientific community continues to explore these concepts, much more research and understanding is needed to determine the feasibility and practicality of utilizing wormholes for these purposes. It is essential to emphasize that our current understanding of physics, particularly regarding wormholes, is limited. Further advancements in our scientific understanding, specifically in areas such as quantum gravity and exotic matter, may shed more light on the feasibility of creating or manipulating wormholes. Until then, the creation of wormholes remains purely speculative and within the realm of theoretical physics and science fiction. Thank you for watching Time Pilgrimage. Please take time to subscribe to our channel and click that notification bell for more thought-provoking content. Until next time, thank you for watching Time Pilgrimage.